If you give me just a few seconds, I can explain parallel universes with the plot behind me. Ready? Here goes. The plot here represents our universe at any time. The past is the cone pointing downwards, and the future is the cone pointing upwards. We're right at the origin at any given instant. We cannot travel outside of this cone. Now, at the time of the Big Bang, you can think of this as the creation of these cones for us. But at the same time, there might have been an infinite number of other cones created that we cannot access. We can't travel to them because they would lie in the space-like region. Because we cannot travel to these potential universes, they're called parallel, like lines that we can never cross. Could a black hole be thought of as its own kind of fundamental particle? Yes. Incredibly, it might not be that inaccurate to say that a black hole is a special kind of fundamental particle. When we think about the fundamental particles of the standard model of particle physics, like electrons and muons and other fundamental particles, these objects often behave like point particles. They don't have a finite extent. They're like infinitesimally small. It's only when these fundamental particles interact with other objects, other types of fundamental particles, that they get a finite volume, like when an electron interacts with the nucleus of an atom to make the volume of like a hydrogen atom. And you might be thinking, well, what about a neutron and a proton? Those have like a radius that's been measured. Well, those are not fundamental particles. The neutron and the proton are actually composed out of quarks and gluons. And quarks and gluons have never been observed go freely about for other reasons, but not only that, but not limited to just the fact that the nature of the gluons is very different than, like, say, the force that describes the electromagnetic force of the electron. The gluon force is the strong force. It's very hard to pull these things apart. Some would say it's infinitely hard. It's still a little bit of a debate, but again, this point-like nature might be one of the reasons for that difficulty. So gluons might behave like point particles too. We don't really know. But the whole point of this is that the black hole is a singular point in space and time. And it's incredible to think that something as complex and different as a black hole might be analogous to an electron or something like that in a weird way, that it has the same spatial extent of being a point. So you could almost think of a black hole as a type of fundamental particle, but you won't see it listed in the standard model of particle physics. Well, why is that? Well, there's a number of reasons. First of all, you can't create a black hole with any other theory of science other than general relativity. And the standard model of particle physics is not compatible with general relativity. So right now, black holes are a general relativistic object outside of the domain of the standard model of particle physics. So that's one reason why you won't hear a black hole called a fundamental particle. But it's interesting to think about. We can also have it that a star actually steals from a gas cloud. So here we have a small cloud of gas that's getting pulled under the gravitational influence of a star. And in actuality, when these mass components of gas get close enough, this system would just capture it. However, this simulation only models gravitational influences. So you'll have to use your imagination a little bit. I do work with high-resolution simulations called Fire simulations, which actually do have the dynamical processes where when the gas gets close enough to the star, it merges and becomes part of the star itself, and the star actually gains mass. But these Barnes-Hut simulations are just a lot simpler, but they're still nice to see. You can see how this gas cloud has been completely engulfed by the star, and in reality, all these gas points would not be hovering, they would just be emerged. The Cartwheel Galaxy is a very distinctive galaxy that was recently imaged by James Webb Space Telescope. Behind me is a simulation of its formation. Now, this was caused by a Milky Way-like galaxy that had a smaller galaxy crash into it, and the gravitational field from the smaller galaxy caused the stars from the Milky Way-like galaxy to get all spun up. This simulation was done by Chris Mijos and Sean Maxwell of Case Western Reserve University, and it shows this incredible process in action. In my new book coming out shortly, I'm going to talk about a disagreement between the Einstein field equations pictured above and the Heisenberg uncertainty principle. While the Einstein field equations say that the gravitational force is due to a mass bending space and time at a precise location, the Heisenberg uncertainty principle says that the precise position and location of an object can never actually be known. There's always a quantum uncertainty due to the effect of the object behaving like a wave. But this is a problem for both theories because we have to know the precise location of an object to know its gravitational effect. For example, an electron would still have a gravitational force associated with it, but if its position is uncertain, that would mean that its bending of space and time is uncertain. So this is a major unresolved problem in physics. There's an incredible triple star system called Alpha Centauri, and it's 4.3 light years away from us. Now, there's 3 stars. The first one is called Alpha Centauri A. It's 1.1 times the mass of the sun, and it's 1.5 times as luminous, so it's brighter than our sun. And the next one is called Alpha Centauri B, and it's 0.9 times the mass of the sun and about half as luminous. These 2 stars are 35 AU away from each other, so they're not the same brightness exactly, but they're very close. And there's also a third star. It's a red dwarf, and it's called Proxima Centauri, and it's 13,000 astronomical units away. So it's way further away than the other 2.